Hey guys, it's Michael and welcome back to Let's Try Hardware Engineering. So, I couldn't help myself and I actually just got to stop paying attention and went ahead and did this next one. But I think that, and I might have done two actually, I think we can reconstruct it here, and I don't really exactly remember what I did. Oh, well, yeah, I guess it kept it, didn't it? Well, what we'll do is we'll just delete it. We'll remove it. And we'll try it out. So we're supposed to design a single full adder, and I shouldn't have probably dismissed the guy here, but they told us about it last time. So we're adding binary numbers, accounting for values carried in as well as out. So a full 1-bit adder adds three 1-bit numbers written as A, B, and carry in, and A and B are the operands, and carry in is the bit carried in from the previous less significant stage, meaning what we did with the half adder, where we added two together. If they were both 1, the result was 0, and we brought the 1 forward. So that's what's happening here. The circuit produces a 2-bit output carry and sum, represented by the signals carry out and sum, where the result is 2 times carry out plus sum. So our inputs are A, B, and carry in, and those are right here. So let's grab those guys. And I tell you, this took me a bit of figuring, looking at the truth table and just trying to figure it out. I don't know the logical method to kind of analyze these problems and figure them out. And I'm sure trial and error isn't the method that hardware engineers really use. Although they're probably using more complete circuits than this in general. Okay, so here's our outputs, sum and carry out. So we've got our two numbers here, our two 1-bit numbers, and our 1-bit in. And then we've got our sum out and our 1-bit out here. And here's our truth table. So here's the problem, right? Here's our three inputs, the first three columns here, and then our two outputs. And I think what we have to do, and the way I solved this earlier, is that we have to kind of break it down a little bit. And I'm sure there's some formulaic way to do this, but I don't know what it is. So what I did was I looked at sum here first, because that's our main output, right? And thinking that we'll deal with the carry later on. So I looked at sum first and sort of thought about it. Every time... Well, first of all, let's skip that. Let's look at A and B, right? There's a couple patterns here that we can see. These last two groups here, A and B, are the same. And they're also both 1. So we're going to get, well, I don't know. They're both 1s. These are both 0s, right? So the middle ones here, though, they're mixed. We've got A being 1 here in these two, and B being 1 here in these two. So if we look at the results of these, though, in this case, it's 1, B is 1, and sum is 1. But in this case, we're bringing in the carry in, and sum is 0. And in this one, we've got basically the same situation. A is 1 here, and sum is 1. But in this one, A is 1, but Cn is also 1, and the sum is 0. And this is bringing me back to the sort of memory about the XOR gate, right? Where if the inputs are mixed, then the output will be 1. And if they're the same, then they're going to be 0. So if we think about sort of combining A and B, right? We could reduce this column to something easier to think about. And if we know that A and B and Cn, the combination of these three, give us the result in S, then we can kind of think about that. So if we took A and B and XOR'd them together, right? Where they're the same, their output is going to be 0. And where their input is different, the output is going to be a 1. So if we think about that, right? Well, let's just do it. If we put an XOR here and we wire it up, now we can just consider this one and this one. This is A and B XOR'd together, and this is C, right? So now we just have two inputs that we want to get up to here to result in that. So how does this work? Let's see. So here, A and B are 0, and Cn is 0, and the sum is 0. I'm sorry, A and B are both 0. XORed together, they would be 0. Cn is 0. Sum would be 0. Okay, well that sounds like an XOR. When they're the same, it's a 0, but it could be lots of different gates. Here, A and B are the same, so there would be a 0. Cn is a 1, and the sum is a 1. Now that definitely sounds like an XOR. We got a 0 here, a 1 here, and our result is a 1. So the next two, both of these XOR, well actually the next four, the result of A and B will be a 1. So a 1 and a 0, output is a 1. Okay. A 1 and a 1, the output is a 0. A 1 and a 0, the output is a 1. A 1 and a 1, the output is a 0. Okay, that sounds an awful lot like another XOR between the AB combo and the Cn. And then finally, on this one, we've got two 1s, so the output for the XOR is a 0, and Cn is a 0, and the output is a 0. Again, the result of an XOR would work for that. And then here, 1 and 1, so the output would be 1, combined with Cn1, XORed together would give us a 1. So I think that, and again, this is how I kind of figured it out before, is that an XOR here will give us the proper output on our data, or on our, what is this, the sum. So we worked that out, I believe. And then what we're left with, let's get rid of this. It's a bit ridiculous, isn't it? Let's just bring that down and put it on there. There we go. That's a lid now. It's a little more direct. So now, if we look at where can we pull a signal off of here to get our carry? What are the conditions where carry is a 1? Well, carry is a 1 when B and Cn, carry in, are 1s. It is a 1 when Cn and A are 1s. It is a 1 when A and B are 1s, and then it is a 1 when everything is a 1. So let's think about that. When everything is a 1, right? Well, let's take the easiest bit here, actually. When A and B are 1. Okay, well, we got A and B. When they're 1s, if we ANDed those together, wouldn't that turn on the carry bit? I think it would. So we could take an AND gate, and let me try to put it somewhere where we can have decent spacing here. So if we take you straight over to here and up, and then maybe from here straight over to here and up. Okay, so there's that one. There's this row at least. The next one is A and Cn. So when A and Cn are 1s, okay. Well, actually, let's narrow it down. When A is 1, B is 0, and Cn is 1. So when A is 1 and B is 1, or actually also this row, when A is 0 and B is 1, but Cn is 1, we're basically getting that right here, right? When one of these is a 1, this is going to be a 1. So we could take it from here and put that over here, and the Cn, when it's a 1, if we put those two things into an AND gate, then we would pass that 1 up into here. So let's try that. What did I just do? You can see these circuits are going to get very messy. Alright, so we took it from there. So now this handles our A and B when one of them is 1. And if we take it, say, from here over, all right, move that up here. Now we've got the output of two AND gates to deal with, so if we OR them together, if either of those conditions is true, then it'll pass through. Right, like that. Okay, now let's just check this and see. For all the conditions where C out is a 1, so the first condition is where A and B are mixed and C in is a 1. So A and B, if they're mixed, we're going to get a high right here, a 1 right here, and so that's going over here, and Cn is a 1, so that's going to go into right here, and it would make this AND gate produce a 1, and it would go through this OR gate, produce a 1, and give us a 1 there. Okay, so right here, we got A and B mixed again, Cn high, so that's exactly the same AND gate there. And then this one, we have A and B being 1s, so the output of this XOR is going to be a 0, and then we have this guy being a 0, Cn being a 0. Do we have that solved? In this one we have them both being 1s, the XOR. Oh, okay, we're taking them before the XOR. Of course we are. When A and B are 1s, down here, looks like any time A and B are a 1, no matter what the condition of C in, we're getting a 1 on C out. So that's why we can just take them from right here, put them into an AND gate, and have it go up to C. Yeah, well, let's see if it works. I think this is the circuit that I built before, but we'll double check. Okay, when everything is 0, both outputs are 0. There's 8 tests here. When carry in is a 1, sum is a 1. Okay, so we got that passing up. It doesn't get through the AND gate because the other condition here isn't met. I don't know if any of that made sense, by the way. I know it was a lot of crazy talk. All right, so here they're not matched, so it goes through that XOR. These aren't matched, so it goes through that XOR, and it doesn't make it up here into the carry. So we just get the output on sum. Here we've got B and carry in being 1s and carry out is a 1, but not the sum. So we do make it through the XOR gate, but we don't make it through right here because Cn is also a 1. But we do make it through this AND gate and up into the carry. And that was apparently the expected output. When A is a 1, we expect sum to be a 1. Yeah, that worked. When A is a 1 and carry in is a 1, we expect carry out to be a 1, just like with the other case where B was high and A was low. When A and B are 1, carry out is a 1. That makes sense. We saw that from before. And so we're just picking up the signals here before the gate even and bringing them up to the carry. And when all of them are 1, we get a 1 on both, which makes sense. So we have completed that puzzle. Now, is there time for the next one? I'm not sure. Oh, okay, right. Actually, this is kind of an easy one. They're telling us about how decimal numbers are represented in binary here, because we have if you consider decimal, right, each digit has 10 different values it could be, whereas with binary we only got 2 different values. So in order to represent a binary number, we have to say that these mean something, and the way that we say that they mean something is by its position raised to the power of 2, just like in decimal, where the position raised by the power of 10 signifies the number. We got 1 times 1, the tens place times 10, the hundreds place times hundreds, etc. So here we have the same thing. We have the 1 times the times 1, right? Is it 1, 2? Yeah, it's 1, 2, 4, 8, 16, 32, etc. So anyway, that's how. So for instance, a 15 is 4 1s in a row, because we have 1 times 1, we have 1 times 2, 1 times 4, and 1 times 8. So 8 and 4 is 12, and 2 is 14, and 1 more is 15. So that's how we calculate that. When you go to 16, then we have to add a new digit to get that. So let's see, what else do we talk about? We talk about using buses here. So we're going to delete this. We'll be given 2 buses of 4 wires, each one carrying a 4-bit number. Your task is to add those numbers and place the result on an output bus of 4 wires. We could do it individually, or we can use the new bus adders that we've been given. So A is a 4-bit wide number. Let's get the grid. Right, so here's our numbers. B is a 4-bit wide number. D is an output, also 4 bits wide. And C is a 1-bit carry. So again, 4 digits can represent up to 15. If we had to carry out, then we'd be popping into the next digit up there, which would make it a 16. So our output is the sum, the carry out. Okay, they don't tell us anything else. That's it. We're on our own here. But there are some new gadgets to look at right here. We've got a half adder, which adds 2 input numbers A and B to produce a sum and carry. Here's a full adder, which adds 2 numbers to give us sum and carry, but it also includes a carry in. And then here's our 4-bit half adder, having a carry in. Let's just put one of these on the table here. I think this one is going to have, 2 4-bit numbers in, 1 4-bit number out, a carry out, and a carry in. We don't have an in here, so let's take the half adder, which doesn't have a carry in. So I think this is the gadget we're going to want. And all we're going to want to do is wire up our 2 4-digit numbers into this guy, wire our carry out into the out, and then wire the output into this. And these are set up so, let's see, the least significant digit is over here, right? So this is 1s, 2s, 4s, 8s, like that. Okay, let's try wiring it up. Why you flip? I don't want you to flip like that. Okay. All right, let's see what this does. Yeah, it's going to want to go backward on me. I don't want it to go backward. So I'm just going to do them like this. This is a quick and dirty circuit, but I don't want the wires to go all haywire on me. So let's just do it a little more by hand. So something like that. Nope. Can you just go like that? Thank you. I mean, I guess I could have taken that little bevel, but so up like that. And I think this might be the easiest circuit we've done, to be honest about it. So we got the output of A going into this guy. We got the output of B going into this guy. We've got the output, the total output going out here, and the carry going right there. And I think that's going to get it for us. Okay, they input 0, 1, 0, 1, and 1, 0, 1, 1. And we got 0, 0, 0 with a carry. Is that right or not? I don't know. I'd have to convert the numbers, I guess. I'm going to trust it. Okay, we got different numbers that time. And a different accurate result. Same with test 3. Test 4 went through okay. And test 5 went through okay. So that worked out okay. So let's take a look at the next thing we're going to get into. This is called complements, and basically it's the beginning of learning how to subtract in binary. And that's what we'll be working on next time. Essentially, it amounts to finding basically the inverse of a binary number in order to negate it. So, do they have a picture here? Yeah, right. So they're essentially adding like 1001 and 0110 to give us 11111, and then inverting that to give us 0000. So, yeah, we'll have to figure that out later. I haven't fully read that thing. So anyway, guys, that's it for this episode, and I will see you next time around. Thanks for joining me, and have a good night, day, whatever it is where you are.